my mind during your introduction. Okay, so I'm going to talk about something called residuality theory. I have planned to talk for much longer than 40 minutes, but we'll see how it goes. So the work that we're going to talk about tonight is part of my PhD. My PhD is based around residuality theory and proving it out. Residuality theory is actually a set of ideas that I've come up with myself as part of my PhD in complexity science and software engineering. Before I was doing these things, I had quite a corporate life, as you can see here, and some of these ideas were born in that arena. A lot of what I'm going to talk about tonight is in this paper, which was published last year, on residuality theory, random simulation of attractor networks. So if Mahmoud asks any difficult questions, I'm just going to use math to make it quiet. And this and a second paper, which is I'm currently working on now. There's a series of papers behind that. We'll look at them towards the end. So the problem that we're trying to solve, what is the problem? And the problem is, why is software architecture so difficult? Why is it so difficult for people to make decisions around what should the structure of this particular application be? And there's some research that's been done on this, and it turns out that when you ask software engineers and architects, how did you make decisions about the structure of this application, but you ask them under conditions of anonymity, where no one will know what they said or who they are honest and they say, we don't know. Everything's based on gut feeling and vibes. We've no idea why we make decisions. It depends on what we've read recently, what we've listened to. It's kind of random. And one of the problems we had, one of the problems that I was tasked with solving at one of my previous jobs was that how do we create architects? How do we take someone who's somehow through some education or circumstance learn how to code? How do we get that person to behave and think and deliver like an architect? And that means make structural decisions based on the environment the software is going to execute in. And the problem with software architecture can be summarized like this. So the problem of software architecture is this, that we have this structure. We have to make a decision about what is the structure of this thing, how many components, where should they live, how should they be linked to each other, how should they talk to each other, all of these things. And that's quite a simple problem to solve, actually. If you have a background in computer science and software engineering, it's actually not that difficult, even if the tech bros like to make it look like this is an incredibly difficult thing to do. It's actually quite easy with a little bit of practice, and it's in the domain of ordered systems. It's predictable, it's mathematical, it's logical, you can reason about it, you can test it. It's in a domain that's entirely in our control. We write the code, we control the machines, we make this thing happen. And what happens then is we take this innocent little machine and we place it into a unpredictable, uncontrollable, unknowable environment, which is a business environment, usually in the first instance, a business environment which lives within a market, which lives within a society. And none of this is controllable or predictable or testable in the same way. And what happens is, as we place this little thing into this complex bubble, things start to happen, unpredictable things, with no real direct relationship between cause and effect. These X's, these things that just pop up. We don't know they're coming, we don't know they're there. They tend to surprise us. And what they do then is they put pressure on this little innocent structure that we've invented and put in it. And what they tend to do is they tear it apart and they make our structural decisions, which we've made as architects about this application, they make them look foolish. And in many cases, we have to tear everything apart, put it all back together again, make our excuses, try again. And a lot of IT projects, a lot of software projects at enterprises tend to fail because of this limitation. And the way that we deal with this in the first instance, because it's quite an overwhelming thing, the way that we deal with this, because there's no way that we can sit down and figure out exactly what every X is going to be in this domain, what we do is we just make the bubble smaller. And we use tools like requirements engineering, where we go around and we ask people, how is this thing going to work? And we limit the world to their description of how it's going to work. And we force them to express themselves in a very, very particular way, and to be very certain about what's going to happen. And we also do this thing called enterprise risk management, where we just make up a bunch of numbers and say that there's an X% chance that this thing is going to happen or that thing's going to happen. And we make the world much smaller. And we reduce our problem to the X's inside this inner bubble, and that makes life easy, and it makes it easy to act. And that's what most people want to see in software projects. It's better to see people acting than to see them sitting around getting stressed about the fact that they can't predict anything. And this gets the ball rolling and solves some problems, but the issue is that eventually something's going to happen out there. This red X, something pops up and we're back into the same problem again, and it will rupture the system, and it will cause us to question the decisions we've made about structure. And if this was always the case, if it always happened in this way and this red X always popped up and always destroyed the system, then the only way to deal with this problem would be to just accept it, build something, throw it out there, wait for something to happen. When it blows up, we just start all over again. And that's called, in the software world, that's called agile. It's also known as winging it. And it's how most of the software industry gets its job done. But there is a subset of architects in the world who continuously, across long careers, deliver software solutions that seem to defy this problem, solutions that survive despite the fact that the environment that they deliver software to is unknowable. And the question that I've tried to answer in my research is, how are they doing this? How do some people continuously get this right? And they get it continuously right in a way that makes it not possible for this to be random or for it to be survivorship bias. It's consistently the same people delivering solutions over the course of long careers. And the question then is, what are they doing? What do they do that's different than the people who aren't cutting it? And how can we make more people able to do this? And before we can do that, we need to know what is it that they're actually doing. And this turns out to be a problem that exists across many, many different professions, which is captured in this book from 1981 by a guy called Donald Shun, that talks about the reflective practitioner. And this is about how that for most jobs in complex domains where things are unpredictable and unknowable, work is not done by following processes or by following a certain kind of practice. It's done by doing things, by reflecting on what you've done, and by learning from different contexts how to apply things in different complex contexts. And this work is related to work that Dewey did about 100 years previously, I think. So the problem that we're dealing with then is one of uncertainty. We don't know what's going to happen in these environments, and that leads us to the complexity sciences. And the complexity sciences are pretty popular right now, especially in management circles. You'll get a lot of hallelujah complexity at various organizations, various methods and techniques and frameworks that help people navigate or manage or reduce or simplify complexity. And a lot of people within the software industry are very skeptical when you talk about complexity, because they're used to seeing these management consultants stand on stages and talk about woo-woo complexity, everything's unpredictable and difficult, and if we all hold hands and sing, it'll be okay. But there's no way to relate these things back to, well, how does it change software engineering? How do we actually do anything different in these contexts? And so what I try to do is to make complexity relevant to software engineering. And so before that, a quick definition. So this innocent, structured, logical, predictable, controllable thing, which is software, it gets to live in this unpredictable, uncontrollable, unknowable bubble, which is the environment that the software has to execute in. And if you're an architect of software systems, then your job involves working in here. And that means knowing all the things that we get taught at college, how, logic and computer science and algorithms and data structures and all of that stuff. And then you've got to bounce out here into the madness where there's people and there's politics and there's economic concerns and there's social structures and there's things we don't understand and can't describe and can't even grasp. And then you've got to bounce back in and do your logic thing and build systems and test them. And you've got to bounce around all the time. And you're constantly moving between these two worlds. And we call this kind of system then a hyperliminal system. So liminal just means that you're in transit between two different things or two different places. And so the architect, the designer of a software system, is constantly bouncing between these two very, very different worlds.
Is that is that definition or is that term given by engineers, or are you importing this term from elsewhere?
I made it up.
You made it up. Okay, because this sounds this sounds a lot like Deleuze and company. So
okay, no, we haven't even
first
got
red
to the
flag.
cool stuff. Yeah. We haven't even got to the cool stuff yet. So this is so these systems mean that we as architects have to move between two very, very different things. And we're only really trained for one of them. We're trained for the little one, for the easy one, for the logical, structured one. No one tells us until we get into the world of work that there's an absolute universe of madness out there that we're never going to be able to grasp or understand. And so then we come to a few other things that we want to talk about, and one of them is Heraclitus, which all of you know, most of you being students of Mahmoud, is the guy who said that no man can ever step in the same river twice because it's not the same man, it's not the same river. And Heraclitus was the guy who then is considered to be one of the first process philosophers who's seen the world as constantly in flux and constantly changing. On the other hand, we have Plato and Aristotle and the Western philosophical tradition since then, which tends to look at objects and substances and ideal forms. And software engineering is very, very much centered on this idea of ideal forms. And if you look into the techniques and the ideas around software engineering over the last 60 years, they have this thing called object orientation, which is basically Plato's ideal forms in code form. We'll find these perfect objects that we'll be able to inherit from and just adjust a little bit in order to build our systems. And so we're deeply, deeply affected by those ideas. And the idea that everything is in constant flux isn't really there in the way that we represent software. It's definitely there in our everyday existence, though. And most software architects then tend to have they don't think about this. They don't think about their philosophy or how they see the world or how they think about the world. And they tend to have an inherited philosophy that they're not even aware of. And that's basically Platonic essentialism, the existence of ideal forms, focus on substance, some degree of structuralism, the belief that if you investigate the language of stakeholders or people in the system, then you will uncover truth about how the system actually works. There's also a lot of naive cybernetics, and by that I mean the idea that this bubble, this business and human structure outside of the software is also a machine, and that follows machine rules with feedback loops and all of those kind of structures. And there's also a very naive understanding of causality, which is very Newtonian, and it's if A, then B, and a huge belief in models, two-dimensional models, being able to represent reality. And collectively, I call this inherited accidental philosophy of software engineering the component metaphor. And it leads to a set of behaviors where people very quickly try to identify structure in a human environment and boil it down to a two-dimensional picture of components talking to each other. And all of these things are based around substance philosophy. What is this thing? What are its properties? How do we map them? What are its relation to the other things around it? And so architecture is essentially representation. And we have to represent the software in some way in order to communicate to developers, this is what we want you to build. But we also have to represent this environment in order to be able to talk about it with other people, gather information about it. And we very often have to do this in a hurry. And it tends to be focused on things like components, business processes, which we turn into a thing with properties and hang properties on it. And these things tend to blind us to what's actually happening in the environment because we rush to represent and reduce so quickly. And Taleb talks about this and calls it the platonic fold. I think someone else defined it. And Deleuze, who we're going to talk about in a while, he calls this blocking, how our obsession with identity of a particular object or substance tends to block us to what's happening around things. And so another concept that I want to bring in, it comes from Kant. And Kant talked about this concept of the nomina and the phenomena. And so the nomina is the Ding an sich, the thing in the world, which is the same thing that we're obsessed with as software engineers. And Kant said that we can't actually know what's there. We have our impression of it, and it's an appearance to us. And this appearance then, which is the green line here, is called the phenomena. And so what I'm adding to this is the distance between the phenomena and the nomina. So whenever something is particularly well behaved, well understood, and we can predict it and we can control it, then we can say that the phenomena are sensing of the thing is very, very close to what the thing actually is, or we can't say that. And in some cases, the thing and our understanding of it are very, very far apart. And so what we get is this thing which I have called the phenomenal gap. There's a gap between the way we experience the thing and what the thing actually is. And whenever that happens, and whenever we have that gap, then we get a lot of confusion because this thing, whatever it is, doesn't do what we expect it to do. It won't react in the way we expect it to, and we can't come up with any natural law or whatever to tell us how we should expect this thing to behave, and it becomes quite difficult. And this is what we're talking about when we're dealing with the complexity sciences. Whenever this particular condition is present, then we get nonlinear effects, things that we don't expect, or we get emergence. Stuff happens that we didn't think was going to happen. That's all emergence is. And there's two particular ways this can occur. One is when we're simply ignorant of what this thing is. We don't know how it works. We haven't done enough work with it, and we haven't experimented with it enough to understand it. And the other is that there's so much going on that this thing is actually complex, and we just can't grasp it because it's changing and moving too fast. And this phenomenal gap then is the thing that's interesting to us. And so the complexity science then is the study of this phenomenal gap. What are these things that don't behave in a way that we expect, that seem to be beyond our grasp? And we have a number of schools of thought here. We have systems thinking, which has its roots in the 1940s and is still going strong. And we have the idea of complex adaptive systems as well. But both of these things, they tend to be just as focused on substance as everything else, except their substance, their thing that they're focused on is called a system, and it has lots of other little things in it. And what they've done is they've tried to resolve complexity or this phenomenal gap as a property of a thing, which is just falling back on the same behavior, the same way of thinking. And other areas of this, in complex adaptive systems, they tend to have a very strong mathematical focus, and you'll find people trying to mathematically map out social systems, which from my perspective is a waste of energy, because it hasn't really given any results. It just gives puzzles. But at the end of the day, complexity science is wildly interesting. It seems really relevant to the problem that we're trying to solve, but it's full of speculation. And there's way too few scientific results, and it seems to be very, very far removed from real world engineering. So how do we use this thing? How do we actually get this thing to be useful to us as engineers? And I found this particular clip from an article that said, what is complexity science? And you'll have to be very, very careful when you're working with these things, because it is very, very easy to slip into the realm of pseudoscience. There's so much speculation, and the barrier for entry into this is very, very low. So anybody can say anything, as long as they have a little bit of charisma on the stage, then they tend to be applauded within the complexity sciences, within the management side of it anyway. And so what I've done then is I've taken a lot of these ideas and things from the complexity sciences, and I've applied a kind of skeptical razor blade to them and boiled it down to something that I feel comfortable with and something that I think has application within the domain of software engineering, and that is residuality theory. And residuality theory is really, really simple. It says this: there is a bunch of stuff, and it's connected to a bunch of other stuff, and it's all moving, and something is going to happen to the stuff, and the stuff is going to be affected, and it's going to change a little bit. And whatever's left over of the stuff after this thing has happened is called the residue. And the residue will keep on moving, nothing will stay still, something else will happen, and the future of the system will be a function of that residue. That's all it is. So that basically that's all we can say about complex systems. Everything else is conjecture. And whenever we're working with these systems, we can't say what this thing is going to be. We don't know what it is. We don't know when it's going to happen. We don't know why. We don't know what it is. We don't know what this thing is going to be. And we're not even entirely sure what the residues are what residues will come out of that. But as architects, as people who design structure, the only thing we have control over is the residue itself. We get to, as software architects, we get to decide how things fall apart, which is the absolute opposite of what software architects think they're doing. They think they're building something, but we're not actually building something. We're deciding how things are going to crumble. It's a completely different thing than building something. And that is a very simple way of thinking about complex systems that allows us, and we're going to see this is a pretty powerful model that allows us to intervene in how we design systems. It has a slight problem in that it's an accidental philosophical position. So when you say these things, you're actually saying a whole bunch of other things. And if you're doing a research project like I am, then you have to go and back these things up. And then you end up having to take all kinds of weird internet philosophy courses to try and understand what's going on. So residuality is actually, it's got three important pillars in terms of philosophical position. One is processuality. It's a process philosophy. It's saying everything is constantly in flux. Everything is constantly moving. It says that criticality is incredibly important, that our system should be critical. And there's also the idea of difference, which we're going to look at in detail. So in 2020 or 2021, I wrote a paper called The Philosophy of Residuality Theory, where I came out really hard against these kind of what I see as Platonic approaches to software around essentialism and structuralist approaches to language that inform this kind of default philosophy of software architects. And I kind of hinted that there's this thing called post-structuralism, and I think there's answers in there. Obviously, bringing post-structuralism and engineering together is a fantastic concoction, and we'll get to that. And postmodernism or post-structuralism, it turns out, is all about the phenomenal gap, all about what Wittgenstein said was nonsense. These people aren't afraid to get stuck in and talk about stuff that isn't logical, isn't structured, it doesn't have any simple logical way to analyze it. And I had this idea that, you know, if you look at, there's one of these people is called Derrida, who has this idea of deconstruction, where we go in and break down structures and question things and question the relationship between things. And if we're trying to break down these rigid ways of thinking that around software architecture and the representation of software architecture, then those ideas are actually quite attractive, because they help us to break things down and question things. And there's a South African philosopher called Paul Cilliers who links the work that Derrida was doing, which is for me, before reading this book, was very abstract and very weird and connected to linguistics and literature, and I never really understood it until Cilliers said that actually Derrida was a complexicist. He was dealing with the complexity of language and trying to say that, look, language is a complex thing. You can't put structure on it. You can't analyze it in the way that we analyze things logically. It's a completely different way of thinking. And that opened my eyes. Actually, these things have a lot in common. And they're both there in the phenomenal gap, trying to figure out things that seem to be beyond our grasp. And of course, all of these ideas, post-structuralism, are being dismissed as fashionable nonsense. And they're very, very far away from what we do every day as engineers. And you will never have met any of these people or any of these ideas in any kind of computer science course ever, which makes it really interesting as well. And so after a while, I came to this guy called Deleuze, who is a French philosopher who wrote it was active in the last century, most active in the late 1960s. And there are many, many similarities between what I was saying with this concept of residuality and what Deleuze talks about in his work. And there's this thing called the Deleuzian dialectic, which is a way of interrogating things, which is very, very close to some of the ideas that we're going to look at later on. But his ideas are very convoluted, they're very contrarian. It's very hard to get him to actually say anything. He never stops and says anything concrete. And he's happy to just, and a lot of these post-structuralist philosophers are very happy to just keep on keeping on and never actually arrive at anything. One of the most important ideas is the way that he talks about difference. And he wrote a book in 1968 called Difference and Repetition. And Deleuze believed that instead of defining a thing by its properties or by its immediate appearance to us, that the way a thing should be defined is in fact through the differences that we notice in the thing as we repeatedly experience it. And so one of the best examples is to talk about a walk. If you go for a walk, then the first time you go for that walk, you'll only pay attention to where's the path, where am I going, where is the thing. The second time you go on the walk, you'll realize that the house in the corner is white. And you'll notice that's a difference, something you didn't notice before. And then the next time you go for a walk, you'll notice that the white house in the corner has a cat. And the next time you go, you'll realize that there's a moose in that field and I need to go a little bit faster when I walk past this field. And all of these differences, every time you take the walk, these differences all add up to become the identity of this walk. And so it's not just a simple thing that you can analyze, give it some properties and start working with it. It's something that you have to experience over and over again repetitively. And the identity of the thing is present in its differences rather than in its actual appearance. And he also talks about a really interesting concept, something called the virtual. And so if we think about, we have this ding and sick, we have this thing in the world, let's say it's a system, we have our understanding of it in this little green circle and there's a gap there. Deleuze talks about this concept of the virtual, which is a concept of all the different possibilities, all the things that could actually happen. And how if we access this virtual and talk about all these potentialities that are there, we can actually build up an understanding of what might happen in the phenomenal gap. So those ideas are really, really important to what we're going to see over the next 20 minutes or so. And so the paradox that we have to face up to here then is that this focus on substance causes us to miss a lot of things. And so we shouldn't focus on substance. But the problem is that as software architects, we have to focus on substance because we have to build something that's actually real and there. So we have to produce a representation of something that's actually going to exist. And so we have this process philosophy, which actually tells us what's going on, and the difference and the repetition are all baked into that. And then we have this substance philosophy, which we have to actually produce as a design at the end of the day. And so to conclude this part, post-structuralism, Deleuzian process philosophy, the complexity sciences, and even if you look around, you see Wittgenstein's gradual softening over his life towards the fuzzy picture, all of these things represent this struggle with this phenomenal gap, which we can't quite grasp and can't quite understand. And essentially, substance metaphysics is not enough, is not a good enough foundation for software engineering. We need to have something else. And process philosophy seems perfect, but it's a load of fluff, and we need something sharper than that to be able to actually do something. And so from there, what we're now going to do is we're going to go and look at software engineering from a complexity perspective and try to bring these two worlds together. And so what we're going to do is we're going to describe the process of software engineering from a complexity perspective. And so one of the tools we use in complexity to work in environments where we perhaps don't know everything is the concept of random simulation. And this, if we have this problem to solve, let's say that we have a square of size x and a circle inside that square, and we're asked, what is the area of this circle? How do we solve this problem? And what normally happens when you ask people to solve this problem who haven't solved it before is that they'll start looking for r, for the radius of the circle, and then they want to do pi r squared, and they want to figure this out. Another way to solve this problem is just to throw darts at it. And so we throw a dart at the shape, and the first dart hits the circle, and the second dart hits the square, but not the circle. And then we can say that roughly half of the darts half of the darts have hit the circle, therefore it's half the area, which is x squared over 2. And we don't need a formula, we don't need to know r, we don't need to be able to measure this thing. We can approximate this by simulating the environment, by simulating points in the picture. And it turns out that if you take a terrible amount of points, a lot of points, you can get very, very accurate answers to this, and you can figure out the area of shapes that aren't even circles, that don't even have any definable form. And random simulation, if we think about what we do in software engineering, when we gather requirements, when we talk to people, when we try to figure out risk, random simulation is actually what we do. My software engineers don't like to think about it like that because they like to think that what we're doing is precise rather than random simulation. The next concept that's important is something called the Kaufman network. This comes from the work of a biologist called Stuart Kauffman in the 1960s, and he built these networks, and they're called random Boolean networks. And so every node in this network is Boolean. That means that it has two possible values, 1 or 0. And so a good way to think about this is to think about these things as light bulbs. So they're either on or off. And every one of these light bulbs has a little function inside it. And that function is randomly decides when you flip the switch for this network, it randomly decides, am I on or am I off, 1 or 0? And it turns out that when you just keep flicking the switch and flicking the switch on this particular network, the number of possible states for the network is 2 to the power of n. And Kauffman ran this experiment with 100,000 light bulbs. And that's a lot of states. Okay, so if you're gathering requirements, that's a lot of things that you have to know about. 2 to the power of 100,000 is more than the number of known atoms in the universe. It's practically impossible. Then he started linking these nodes together. He started making them dependent on each other, and he started making the function of one node dependent on the output of another. And then he ran the same experiment again, and he noticed something strange, that the system kept returning to the same states over and over and over again. It would return to the same states. And it turned out that when you connect the system with a small number of nodes, that it would arrive at root n, or in this case, 317 particular states. And that's a lot easier to work with, and it explains how we as people can actually navigate complex systems, because the systems, they constrain each other, the elements in the system constrain each other, and they return to the same attractors. These things are called attractors over and over and over again. And that's something that's going to be important to us. And he added another layer to this, something that I call an NKP analysis, where we can actually analyze these networks. And we can say, in this case, N is the number of nodes. In this case, it's 12. K is a measure of the number of connections in the network. In this case, we're looking at the maximum number of connections, and that's 3 on this node here. And a third value is P, and P is bias in the network. And bias means that if this node sends a message this way 50% of the time and this way 50% of the time, it has no bias at all. And it's kind of democratic. But if it sends a message this way 95% of the time and this way 5% of the time, then we can say that it's biased towards this particular course of action. And if you raise n, the number of attractors increases, and the system it appears to us to have a bigger phenomenal gap, to be unstable. If you raise k, then it becomes even more unstable, and the path to a particular attractor becomes unstable. And he found that if you raise p, then the system becomes more stable. And so these three things are levers to introduce stability to a system. And if you scrape away all the layers of nonsense in most software engineering methodologies, if you're familiar with any of those, then what you'll find is that this NKP analysis is actually there in all of them. This is mostly what software engineers do. And so all software engineering, from a complexity perspective, can be described as a two-step algorithm: a random simulation of an environment followed by an NKP analysis of potential structures. So with that, we can combine these things with residuality theory to produce something that might actually be useful. And one of the things that Kauffman talks about then, which is really important to residuality, is the concept of criticality. And in criticality, we, let's say, have a little graph of n, which is the number of nodes, and k, which is the number of links. And if you have a very small number of n and a very small number of k, then you tend to have a system that's incredibly ordered, easy to understand, predictable, controllable. As n and k increase to a certain level, the system becomes chaotic. We can't understand it, we can't manage it, we can't predict it. The phenomenal gap grows as you move between these two red dots. And Kauffman then describes this line that exists here, which is commonly known as the edge of chaos, but I hate that term. And this is criticality. And when a system exists on this line, when it has criticality at a certain number of n, a certain number of k, a system is relatively stable, relatively ordered, a relatively small number of attractors, but it has the ability to react to things that it hasn't seen before. It has the ability to change and has more options, essentially. And that seems quite mathematically obvious. And what tends to happen is when a system is born, it's quite simple and NK are quite low, it will be stressed by the environment, just like this thing that happens in residuality. And the residue, the system will break apart and reform. And it will break apart and reform and break apart and reform as these things happen. And eventually it will either die from this consistent happening of things, or it will move toward this edge, this criticality. And once we get to criticality, then we have a system that's going to be able to respond to its environment in a completely different way if it survives that far. And it turns out that we can actually put them to do this without spending a great deal of money. And so what we do is we realize now that we don't need to think about this entire bubble. We don't need to worry about every X or every element inside that. We don't need to go around and capture every object and list all its properties and all its possibilities. We only really need to deal with a certain number of attractors. And instead of designing a system just to meet one particular attractor, which is usually a functional attractor, we have to design a system to live in a series of attractors. But how do we know what they are? Well, what we do is we randomly simulate the environment and we come up with these X's, things we call stressors. And that can be anything from a system goes down to a change in the dollar-euro exchange rate, to the behavior of a competitor, to a change in social attitude. And then what we do is we talk about this attractor. What does it look like? Does our system survive in this attractor? And we look at our software and we say, well, these two components won't work anymore. But if we had this little green component, the system would survive inside this attractor. And so we call that residue number one, and we put it over here. And then we do the same thing again with a different stressor and a different stressor. And eventually what we end up with is a naive architecture that we started out with, defined by the component metaphor, the way we normally do things, and a whole bunch of residual architectures which are slightly changed. And these are all these differences that we talked about, that we find in Deleuze's philosophy. And what we then do is we pull all of these together into a coherent architecture. And that architecture, it turns out, will show signs of being able to survive things that it wasn't designed for, because we're forcing it to do this walk through to criticality. And we can actually prove that that happens. The reason this works is because we have a mathematical leverage at play. Every residue, it turns out, usually survives in several attractors. Every attractor has a large number of potential X's that will push the system into that attractor. And we only have to get lucky once. We only have to find one stressor that will identify one attractor that identifies the residue. And that means that we will solve for all of these potential stressors, all of these things that can potentially happen in the environment. And all of these things we might not even be able to describe or see or understand at a particular point in time. This turns out to be difficult to get people to do this kind of stressor analysis because of something called the curse of high dimensionality, where we tend to focus on things that we think are highly probable. And that's a behavior that becomes exacerbated by being in the presence of other people where we don't want to look stupid. And so one of the things that I do with students and with groups who are trying to do this work is to bring in the idea of ridiculous stressors, such as giant fire-breathing lizards are going to come and destroy your city. What's the residue? What's left over? And that seems ridiculous, right? Because the probability of this happening is very, very, very low. And the point of this example is that probability doesn't matter when we're dealing with these things. It doesn't matter if you consider something to be probable or not. It just needs to give you information about what kind of potential attractor states can exist here. If you solve for lizards, you solve for fire and flooding and earthquake and invasion and pandemic and all of those things that can make a city not function like a city anymore. And so probability is something that we need to get away from. So to give you a...
Hey, Barry, can I just ask you one thing, just, for this last slide, I mean, it's intriguing. I just, appreciate very much what you say. But I understand, if you solve for Godzilla, you solve for fire and flooding and everything else, right? But if you solve for flooding, you obviously don't solve for fire and you don't solve for Godzilla. So what you marked here as this 1x that solves everything is almost like your imagination must be, is it the worst case that you actually try to solve for? Is it like, the ultimate stressor? Because, they're not all the same, obviously. As I said, if you solve for flooding, you don't solve for Godzilla, obviously not, right? So what is there anything that you can say about, how you select this?
Yes. In a few slides, we'll go into detail. We'll go into detail around that. We'll come back to that, Rudy. So here's an example of how this actually works. And this is taken from a bunch of real world systems that I've amalgamated. And so what we're doing is we're building a system that's going to manage a network of fast chargers for electric cars, which is global. So you have a central software system that manages how we interact with these. And the way this works is, in the initial version, customers sign up online. They register as a customer. We send them a little key fob, which is smart. They drive up to the charger. They hold up the key fob. It registers who they are, sends a message up to a back-end system. The back-end system sends a message down to the charger saying, yes, this person's allowed to charge, paid their subscription. And this is the kind of stressor analysis that we run. And this is a cleaned up one. And what we do then is we come up with a bunch of stressors. We talk about what impact is this thing going to have? What do we have to change in the residue in terms of the business? And what do we have to change in the residue in terms of the technology? And there's the pattern here is what we want to see. And so if we look at stressor number 3, we have this idea of a field login. So, and this happens a lot. These little key fobs, they don't work particularly well. They're sensitive to heat and cold and magnets and all of those things. And whenever that happens, what's the residue? Well, the residue is that you have a very angry customer in their Tesla, parked in front of the charger. They can't go anywhere. This isn't good. So how do we change that? Well, it turns out that we have to actually change in terms of business model. And what we do is we use a little bit of technology, automatic license plate recognition. And instead of the key fob, we read someone's license plates. We allow everyone to charge so that we don't have this nasty residue with people stuck in queues and all of that stuff. And then we send an invoice later on to their home address or when they register their car. The next thing we look at is stressor number 8, where there is going to be some damage to the car or damage to the car charger, either accidental, people drive into these things or some form of vandalism. And we solve this with redundancy. Let's have some extra things, and let's have security cameras to make sure that if someone does something to the chargers, we have them on camera. And the next thing is stressor number 12. What happens when a customer abandons their car in the slot and just goes away? And this is a big problem at golf courses, right? People will plug in the car and they'll disappear for like 8 or 12 hours, and then the asset is blocked. No one else can plug in. How do we solve that problem? We already have something here, ALPR, automatic license plate recognition, and we have a sliding scale invoice per minute. So the longer you're away, for your second 25 minutes, it costs even more. The next 25 minutes costs even more. And at that point, we actually make a bigger profit if someone does this. And people won't do it as often because they don't want to pay that much money. And that's all standard business development, standard architecture stuff. The interesting thing happens when we look at stressor number 14. Stressor number 14 is something called icing. It's one of those X's that nobody ever sees, that nobody could possibly predict or know in the environment. Icing is whenever people who drive ICE, so internal combustion engine or fossil fuel cars, decide that owning an electric car is actually a political position. And I don't like people with that political position. So I'm going to park my pickup truck in front of the charger so that none of these people can actually charge their electric cars. And this all comes out of toxicity on Twitter and all of those things. And there's no way you could know that this was actually going to happen. But it turns out a combination of the residues that we put together for 12, 3, and 8 means that this doesn't affect us. This thing that we couldn't have seen, that we couldn't possibly have predicted, doesn't affect us because firstly, we'll have their license plate. Secondly, we have redundancy, so we don't care. Thirdly, we have them on camera, so we can make a police report. And fourth, we're going to charge them an awful lot of money if they park there for longer than 25 minutes. So the problem is already solved. And this is an example of criticality. And this is a pattern that you see again and again and again when you use this approach to architecting your software systems. And the problem was one, obviously, that turned up in America first, but it's also come to Europe now. And this is an example from Munich, where along the same lines, people have assumed that there's a connection between electric cars and vegetarianism. So they've started to shove mincemeat into the chargers. This is the kind of thing that's not on your requirements. It's not in your risk register. This never turns out. You're never going to catch this. And you need an architecture that has criticality to be able to survive this kind of thing. Finally, then, we come to Rudy's question. And the important thing to remember is that these particular stressors, the stressors don't matter. Okay? So flooding, lizards, mincemeat, whatever, they don't matter. It's the identification of a tractor and the criticality that emerges in the architecture. That's what we're trying to get to. And we use this thing called contagion analysis to figure that out. And so one of the things that we're looking for is that whenever we have stress on a software structure, what we tend to see is that the stressors will sometimes hit more than one component. And you can see that in this case, we're hitting C and we're hitting G. And if you know anything about software and you look at this diagram, you'll immediately see that C and G are pretty much decoupled. They don't have any connection to each other. But if you work in network science, and then you'll know that once that stressor is connected to C and it's connected to G, that implies that C is actually connected to G. These things are connected. There's a coupling between them. And it turns out that there's lots and lots and lots of this coupling that our stressor analysis helps us to uncover. And that coupling, because it's not functional, is actually non-functional. And capturing non-functional requirements is one of the most difficult things that an architect can do within a software project. And so what we then do is we run something called contagion analysis, which uses the concept of, uses matrices, so it's essentially networks, to map out our component structures. And the first thing we do is we map in terms of flow or component or function. We map out dependencies and we look for simple relationships. Like this is a process, a business process, a straightforward business process of that. Here we see systems where you have this mirroring across this middle line, and we're doubling K, we're growing complexity in the system. And these things are very close to something called DSMs, or design structure matrices, and that's what MIT used to design airplanes and spaceships and things like that. The real magic happens in something called an incidence matrix. The incidence matrix, we take our potential component structure and we map it against the stressors that we've come up with. And what happens is, this gives us a lot of information. Firstly, if you see two things that are connected by the same stressor, then you have an example of this hyperliminal coupling. And if they don't turn up in the adjacency matrices, then you know you've identified non-functional requirements, something that needs your attention. Another thing we notice is stressors that tend to cause a lot of damage are things that we should pay attention to. These are attractors that are dangerous for us, and also components or functions or flows that get damaged very, very easily. They need to be protected in a different way in the architecture. And finally, anything that has a similar structure, a similar response to stress, has exactly the same non-functional requirements. That means it gets to live in the same house, because these things live and die together anyway. And this is actually a way for us to make decisions about component boundaries. And this is an actual method for doing that, rather than just pulling these things out of the air, which is what 99% of software engineers are doing today. So this one simple matrix is what we've been working towards the whole time. And this allows us to create a structure for our software in a roughly scientific way that allows, that will show signs of criticality. And to show signs of to prove that that criticality is there, we can run at the final step of this an empirical proof. So we take our naive architecture, we take a list of stressors, and we design a residual architecture, which is what we've done with this thing. But we keep half of our stressors over. And if you've done any machine learning, which I think, Sharif, some of you have done, then you'll recognize this as training and testing. And so what we do is we've trained our system, we have our residual architecture, and we run these red stressors, these extra stressors over it. And we run it over the naive architecture. And if it wins, if it survives each stressor, then we give it a point. And we add all those points up, and we call that X. And we do the same thing with the residual architecture. And if we have a position where both of them fail to survive a particular stressor, the one that is best placed, the one that's most critical, the one that requires the least amount of work, least amount of effort to bring to a point of being useful again, it gets the point. And then we work out this thing called the residual index, y minus x over s, and which is going to be somewhere between -1 and 1. And if that's greater than 0, then we've actually moved up towards that line of criticality. We've done something useful. And so if you're a software architect, having something that can prove that you've actually been useful, you'll know is a huge step forward. It's something that's quite difficult for us to prove. So what this essentially is a new theory of software engineering, which has taken a bunch of ideas from post-structuralism and complexity sciences and fused them together with real-world experience to produce something that isn't only coherent, but can also be tested and proven to work within the world of software engineering. Obviously, you can apply this to other things, but I would say, be very, very careful with that. It's incredibly dangerous to assume that this is going to work in other contexts than software engineering. There's a bunch of papers, like I said, and this is my contact details for anyone who wants to reach out with any questions or anything. But I'll hand over to Mahmoud then for questions.
Yeah, thank you very much. This has been interesting, even though you mentioned all the people I don't like, for example, Hegel and Deleuze and Derrida and all that jazz. But see, this is something I've been struggling with up to a certain point, because we're talking, and Rudy here mentioned Feuerabend up to a certain point during the talk. And I've always been thinking about the uncertainty, not necessarily within the realm of software engineering. And then people like Talib talk about Black Swan and stuff like that. But my question is, if this is already kind of like, human beings know that there are things they cannot predict. Know that there will always be black swans, there will always be there will always be extreme risks emerging from systems that humans develop, software or otherwise, and that there is the predictable world and then the unpredictable world, and what we're trying to do is hedge all our risk in order not to blow up. So my question is this not the case already? Like, do we not already know this thing? Like, why do we need a new theory in this in order to, like, I don't know if I'm making sense. Like, because I once had this idea for something similar, and then everyone was like, well, but we already know that. Like, so the question here is this different in terms of applications? Because also Rudy asked this question, like, how can we Like you have to have this weird, very creative imagination in order to come up with the worst case scenario. Like we know worst case, and we have to hedge for worst case scenarios, but then I don't know, you come to a point whereby you'll be like, well, but is it really gonna happen? I mean, we can, I don't know, the musings of my own, because I don't know how to pinpoint that in a different way.
Yeah. Okay. So I'll answer the 5 or 6 questions I think you're
yes.
So I think one of the things that happens at any large enterprise or any project that happens is that we'll say we're going to build this thing, and then we'll do this thing called due diligence or risk management, and as part of that, we'll use something called scenario planning. Scenario planning is very much a standard approach within software architecture, standard approach within any business, any reasonably mature business endeavor. And scenario planning tends to be stuck in this old world of thinking, and people tend to then look into the past and say, well, this happened here and this happened here, and so we're going to plan for this particular scenario, and it gets very stuck and it gets very turgid, and people tend to miss things all the time. And the evidence of this is, that 83%, if you believe the statistics, 83% of software projects are severely challenged. They don't make it, and they don't make it because they fail to predict what's actually going to happen in the environment. And not over a longer period of time. They fail to predict what's going to happen 6 weeks from now, which is why those software projects will tend to fail. And so scenario planning tends to be incredibly weak. And then you can take a sort of Talebian perspective and say, well, okay, let's take the scenario planning, but let's make it worse, right? And let's make it extreme. And then you get into discussions with managers and with people who own the resources who say, but that's never going to happen. That's never happened before. It's never going to happen. We're not going to spend any money on that. And so we resolutely fail to predict what kind of scenarios our systems are going to be exposed to. That's the first point. The second thing is that the structure of the software system is arbitrary. There's no relationship between the software system structure and what's actually going to happen in the future. And there's research on this. So software structures are generally arbitrary, even if software engineers don't want to admit that to an interviewer or to themselves. And what these ideas do is, firstly, they get rid of scenario planning and they say the probability doesn't matter. The identification of as many attractors as possible is what we're trying to do. And the actual stressors, the things that we're talking about, the flooding or the lizards or the behavior of a competitor, those things don't actually matter. We're just trying to talk about attractors. What kind of structures can exist in this system across time? It doesn't matter how the system gets there. So all of the stressors that we produce at the end of this, we throw them away. We don't actually care about them. They're just ways of generating our imagination, of generating a discussion about possible structures. And so what we're actually doing then with residuality is that we're taking the arbitrary software structure and we're mapping it to potential attractor network structures that can exist within this environment. It's a completely different way of thinking about things. And the architectures that it produces are incredibly different than standard architectures. But one of the most important things that I've noticed across the course of this work is that when I'm talking to senior architects, people who build very, very big things, and showing them this work and showing them the differences and all the little residues and how they're molded together, the senior architects will say, actually, this is what we do. This is exactly what we do. But we don't have any words to describe this because we're not taught anything about any of these things. You know, we're not taught to think along these lines. We just do. And if you do these things often enough and you're lucky and you're exposed to the right projects, you build up a sense for how you do these things. But you can't explain it to junior architects, which is one of the big problems our industry has. We can't make junior architects because a senior architect can't articulate what they do. And, you know, 10 years ago when I first got the question, or, you know, teach these people, make junior architects, I had to leave the room, take a deep breath and say, I have absolutely no idea how I do what I do every day. I don't know what I am. I don't know how I get these results. And so the last 10 years have been a journey of me trying to figure out what goes on in my head. And this is it. And it turns out other senior architects, when they see this, they say, yeah, this kind of happens in my head too.
I see. So it's basically, you're basically articulating, this is where I think the book comes in, The Reflective Practitioner. So you're basically trying to articulate the things that you guys do right without even knowing how to talk about them.
Yeah.
Interesting.
Yeah. Yeah.
Yeah. So it's not the other way around. Like, you're not saying, okay, here, this is the solution. You're basically saying the solution that these people are putting out there makes sense, and I'm trying to theorize it. And yeah, it's in the title, Residuality Theory, but it's kind of, yeah, okay.
Yeah. And if you give these ideas to a junior architect, you should hopefully save them 10 years of suffering.
See, this is something similar to also from a philosophical perspective to people like Plato, because like this is basically the form that he talks about. It's not something that you can probably, maybe here I'm going to be destroying your entire presentation in one comment, but it's like, so one part of understanding Plato, or one aspect or one way of understanding Plato's theory forms is that it really, and I'm butchering Plato here, but just to make the case, like to make things easier to relate to now. And it's like, this is basically what Plato was grappling with. How can you teach others these abstract concepts? And you need a lot of practice, and you need a lot of practice in dialectics and these discussions and conversations in order to get there. So in this sense, the more senior you are, the more you know what you're talking about. But then it becomes, it's always kind of difficult to get those who are just starting their journey to know what you're talking about, because it takes a lot of time and a lot of back and forth. So maybe is this something similar here we're doing?
In a way, yes. In a way, yeah, I guess these ideas, you know, architects will recognize what we're saying here, and they'll recognize that this is similar to what I do, but they will never use these words.
This is basically this is what Plato was grappling with. Okay, so we have. But we can discuss this aside. We have Nick raised his hand, and then Shrif. So, hi, Nick.
I believe Shrif actually put their hand up first. So, Shrif, if you'd like to go first.
No, don't worry. Go ahead. Don't worry. I'm going to take a little bit long. So, yeah, just go ahead.
Barry, good to see you. Thanks for the presentation. I'm curious as to your thoughts about, and you know, maybe I'll take this a little different from Plato, but actually his student Aristotle, and the concept of the attractors here, and what would you think of them as telai or telos, various telos of the architected structure, their goals, their things to which we are attracted. So a classic one for Aristotle would be that we're supposed to be attracted to virtue. We can more or less get to it, but we can never actually attain perfect virtue. Do you think that thinking of attractors as goals of the architecture to be approached over time and to be sort of, I don't know, like a gravitational pull almost, but with a limit, that would be a fair way to think of think of these within the structure?
No, I had never thought of it in that sense. I wouldn't see them as goals, because an attractor, for example, in a business, a major attractor that exists for many businesses is bankruptcy, and that's very rarely a goal, and unless you're Elon Musk. But it's an attractor is just a phase state of a system that it actually has the potential to arrive in. It's not necessarily a good thing or a bad thing, and it's generally not driven by any kind of rational causality. It's not new. It's very rare, I believe, that in a business system that we plan and say we're going to reach this particular goal. There's lots and lots of stuff bouncing around, and we arrive in an attractor. Not always it's not always a choice, it's not always understood, and a lot of times it's a surprise. You'll notice my work is entirely free of the word goal or purpose. I'm not sure I believe in those things. So I don't see this as being anything that the architect actually intends.
Okay.
Because and from a long career, I would say that what the architect intends never actually happens. So we have to work for a world where different things are going to happen.
For the record, I agree with you with that assessment that we should not think of this as like a conscious goals or even something that the thing about a telos for Aristotle is that it is an ideal. It's not actually attainable. It's an idealism that is used to explain in retrospect the behavior of a given system under observation. And so I think that it seems to me what you're describing here is once you've got a system or a structure, what does it tend towards? And what are these various focal points within it and you've managed to define those rigorously, which is quite impressive. Quite impressive.
I think if actually going back to what I just said, but the one goal that I think that I as an architect have, and I think is fairly clear actually from the last slide, is that is criticality. I'm trying to get to criticality rather than a correct architecture, because I think we've been torturing ourselves for decades trying to get to correct solutions within IT, and obviously you can get to correct if your jobs are right formulas in Excel. But if you're building a large-scale distributed systems within a moving market, then correct doesn't exist, and criticality is what we should see as correct. But that doesn't line up with the mathematical idea of precision and correctness that is maybe expected if you've done a very mathematically heavy education, which is sort of most people within tech that we have to deal with have that expectation of correctness.
Okay, are you done, Nick? Can I go on? Yeah, okay, thanks. Okay, so Barry, first I have a question. You talked about the Kaufman networks. Is this the same Stuart Kaufman that wrote Reinventing the Sacred?
I think I haven't read Reinventing the Sacred, but it is, yeah.
He's a biologist he studied biology, or he's a doctor. He's a medical doctor, right?
He's a biologist, but he did a lot of his work with the Santa Fe Institute.
Yeah, okay. So the same person, yeah. Because I've read this book last year, and I think was one of the best books I've read last year. Yeah, I was just like making sure that we're talking about the same person.
Did you read it in a week?
Possibly, I think, yeah. And I translated actually like the piece of the introduction just for fun for me.
Yeah. So two other books, Sharif, that you'll enjoy even more. One is Origins of Order, and the other is At Home in the Universe.
Origins of Order and what?
At Home in the Universe,
Okay.
where he goes more into the models that I was talking about.
Okay, I'll check these out. So I have like a couple of more questions. So if I understand you correctly, what you're trying to suggest here is to approach how you design your software system or something like this. Let's talk about scale. For example, if I'm building something really simple, I'm going to just like think about the different scenarios that I'm going to be put into, and I'm going to handle these with something called exceptions and catching these exceptions to handle these errors or something like this. But this is for the small scale side of things. But if you're talking about very large scales and interacting with very dynamic systems, like, as you said, society and people with really weird behavior or something like this, it's not enough to study the possible scenarios, because you cannot really know all the possible scenarios, because you can't know all the variables in the environment. So what you're suggesting is to simulate all of the improbable environmental factors, and to throw it at the system, to stress it enough and try to improve the system and to improve its structure into something that can handle all of these stresses, or at least can handle some of them, so that when something really unknown and something that's unprecedented in the history or something like this happens, you can at least bet on your system that it's going to be at least resilient, or can be or have a chance of surviving, like compared to other systems that are not stressed against these things, right? Is that what you're proposing? Yeah. Okay.
Yeah.
So my question again is, and I'm sure you're familiar with Talib and this mediocre stand versus extremist stand thing. So I'm trying to think about the simulating all of these unfamiliar things. And I have an example. For example, like think about companies that were developing protocols for sharing files, like, or not protocols for sharing files, but sorry, hard drives that can carry more space, that has more space to carry more files on it, to share and to make it even more carryable, if you can say. And then boom, they've got the internet out of nowhere, and someone invented file sharing protocols, and all of their like efforts are simply like they're just gone to with the wind, right? Because file sharing systems is like something nobody could have guessed that someone would come up with something like this. So even if I simulated all of the possible or all of the unfamiliar situations, like if I managed to list all of the things that have a probability of 0.0001% and simulate a situation where I stress my system against these probabilities, I might have still not survived something like file sharing protocol if I'm in the business of developing more usable hard drives or something like this. So how does it apply here?
Yeah, so firstly, what our goal is criticality, and our goal can't be that we're going to build systems that are bulletproof, that are going to survive absolutely everything. In the example that you gave, criticality doesn't exist at the technical level; it exists at the business level. So if if you're investing capital into this kind of project and it suddenly becomes irrelevant because of a new technology, then the criticality should exist in diversification of your investments across different companies. Everything is going to die. Every system that we build as architects has a limited life. Eventually, it's going to be made irrelevant by some kind of change in the environment. And we can't avoid that. But we can't make the systems live a little bit longer, and we can't justify the structure of the system in relation to the environment that it's going to live in. what we find is that we don't have to list every single stressor, every single potentiality, everything that might actually happen in the system. What you find is that once you get a system to criticality, then your job as an architect is done, and you don't need the entire list of every single potentiality in an environment to get a system to criticality. You just need to push it around into enough attractors, so that the criticality emerges in the structure of the software, and that's the best we can do as architects in the world that we live in with the information that we have access to. So this is an extended step beyond gathering requirements or working with what we already know.
Okay, so two follow-up questions here. First, I'm just going to throw both of them and then let you talk, because this probably will be my last questions here. So how do we know that our system achieved criticality? Is there like a mathematical way to know exactly if we did this or not?
Yeah, what you'll find is, so I'll just answer that directly. As you move through your list of stressors, as you move through them, you change your residues as you move along, you eventually get to a point where you can't stress the system anymore, where everything that everyone comes up with, everything that you throw at the system will start to eat up those stressors, and you'll start to realize that, oh, when we made this change, when we broke this boundary and moved these functions out here, we created the grounds for a system that can be changed to cope with this. And so that's how you know, it starts to loop. And so that stressor number 14 was just an example. That becomes a repetitive pattern as you move through the list.
Okay, so my other question is, this simulation of lower probability events and simulating stressors and something like this, in a large production setting, these are going to cost a lot of money. We're talking about computing power, we're talking about time, we're talking about resources and everything like this. So if I am in a business and I'm trying to convince my stakeholders that, okay, we need to do this to actually survive something that might be unprecedented, and they're like, how to convince them of something like this? And if I actually do this, okay, so this is going to eat into my profits somehow, at least. This is going to eat into my profit and make me less competitive, because I cannot reuse this profit into investment into new resources or something like this. So at what point simulating these things are going to be a bad outcome, because I'm going out of competition here because other companies don't do this, and this unprecedented event is, we don't know when exactly it's going to happen. So I might go on with these simulations for 5 years and nothing happens. I'm just burning through my profits while others are ignoring all of this, well, which in the long run is not going to affect, is going to affect them really deeply. But in the short term, it's affecting me more than them. If I go out of business at this time, then all of this is what not pointless, but it's really good idea, but you really need a lot of funds for this, right?
Yeah, so this is one of the first questions that usually comes up from developers who are always afraid of this kind of work. So firstly, what this will solve on the level of things that don't cost any money is, you have a bunch of components in your system. How many components should you have? How many functions should there be in each component? How should they relate to each other? Where should they be installed? And how should they communicate with each other? Those decisions are most of the time entirely arbitrary, based on trends, based on nonsense. And this methodology will help you make those decisions. And those decisions cost nothing. And the vast majority of people within your business, people who are making spending decisions, they have no clue how many components, where the boundaries are, which function is moved across which boundary in order to enable criticality in which direction. They don't understand these things, and neither do most developers. So we're improving that. And one of the things that will come up in this is that you will find things that when you run it and you look at the attractor, for example, lizards, let's say lizards destroy Amsterdam and that's where our business is based. And then you're going to say, well, the way to solve this residue is to build a solution in Brussels, far away, far enough away, and that's going to double the cost. And the job of the architect then is to say, well, this is a residue, this is an attractor, and it is a doubled cost. And so what you have to do then is do a little bit of extra work and say, okay, well, what other stress? Well, they're not going to buy lizards, right? We're not going to go to them with that, but what other stressors are there that feed into this same attractor that might seem relevant? And then you have to do real standard architectural work. What is the cost of ignoring this problem? Okay, what is the cost of downtime in terms of income during downtime, in terms of brand reputation, and all of those things that we have to think about? And then you're back to doing real architectural work, which we should be doing every day with the business, and sitting down with them and saying, well, here's a scenario that might actually happen. Here's what it will cost to fix, and here's what we believe it will cost to remedy. That doesn't mean that we have to do it. And we can always say that, okay, look, we're not going to build this thing in Brussels, but we're going to design our architecture in such a way that if this should happen, we can have it up and running in Brussels within X amount of time. And so sometimes you have to counter that residual design. What is the difference? What is this residue? It has to be, what's the English word? It has to be done in terms of the other constraints within the business, which are sometimes financial, but it's much less of a big deal than what people think it is. And what I find is, so a lot of my work as an IT consultant these days involves going in and rescuing projects that have crashed really, really badly. And a lot of times I'll find developers and architects who said, yeah, we didn't want to think about that because it would have cost too much money, and we assumed that the business would have said no. And now you're in the ditch, everything's crashed, everyone hates you, your architecture is obviously terrible, all because you were afraid to bring up anything that might actually cost money. And that kind of thinking, that puts us into that little red circle, and it stops us from reaching criticality in our architectures. So,
I get it. Yeah. So you're basically something like Plato when he said, like, let's make statesmen philosophers. You want to make businessmen software architects, so that they can understand the cost of this and understand why it's important, other than like businessmen who don't have a clue.
Yes. Yeah.
Great. Thanks.
Yes.
So one thing that I was going to add on to this conversation with is actually a reference that I've spoken about a little bit with Barry before, which is the work of Gilbert Simondon, in particular his work on the mode of existence of technical objects. So
come again, Simondon? Did you just mention Simondon?
Yes.
Oh my God.
Yes, Simondon. Yeah.
You guys have put together a list of all the people I wouldn't want
who you can't stand.
The gang's all here, Mahmoud. I brought them in.
Oh my God, you are but sorry, go ahead.
So the way that I sort of see what Barry's done here is Gilbert Simondon has this concept of technicity, and that technical objects can have a greater or lesser degree of technicity, which is their sort of perfection. You could think of it that way. They're more or less complete. They're stable. They can be better or worse instruments or technical objects, depending on whether or not they have a higher or lower degree of technicity. And Simondon thinks that for-profit businesses are actually in a bad position to achieve great technical objects, well-designed, well-built technical objects of higher degrees of technicity, which is something that Barry's figured out how to put a number on here with this work, and particularly with software objects, digital objects like this, because they will be pulled in part by the cost to the business they will oftentimes cut corners in order to and produce objects with lesser technicity because of the relative costs of it. And so what Barry is sort of doing is actually aligning with Simondon and a critique of capitalism for the sake of producing better technical objects, if you want to think of it that way. So that's what I would suggest Barry is actually doing here, is actually critiquing the profit motive with that answer.
Okay, fair enough. There's a question here from Telmo who says that it gives very different examples from traditional approaches. So the difference is, and so a comment there from Telmo as well. There's nothing there in the car charging example that you wouldn't have come up with from a traditional approach. And yeah, those three residues that I talked about. I mean, as I said, that's standard business development, but the example isn't about those particular things. It's about the pattern that we see where we start to see criticality. And traditional approaches don't look for criticality in the way that they're taught. Now, that doesn't mean that every architect out there isn't looking for criticality or isn't doing something very similar to looking for criticality without being able to put those words on it. The things that turn out different is that if you follow the matrix approaches that I showed, you'll find yourself violating, if you're coming from a software background, Telmo, you'll find yourself violating things like solid principles fairly regularly, and very quickly come to the conclusion that those are pretty useless as well, because we're looking at a completely different set of ideas. So what you tend to find as well is that you have roughly an 83% failure rate in our industry, and the traditional approaches that we've investigated, that we teach, don't seem to work. Whereas this seems to work fairly regularly and is actually being put to the wall in terms of empirical testing and research. So I think that those are the main differences with a traditional approach. One of the things I'm hoping to find in my research is that this residual index it's always positive when I've run the experiment with different groups. I'm always getting positive residual indexes, which is proof that this works. What I'm hoping to get is residual indexes that are a lot closer to zero. And I would expect, my expectation is that if you have a very senior architect who's been around the block, who's done all of these things, that their first architecture, their naive architecture, is going to already be residual because they know how to do this. I haven't actually got that to happen in reality yet, but I think it would be interesting to see. Rudy and Albert have their hands up.
And go away.
Sorry, I thought you were first, but
Okay.
Okay. Well, first, thanks for the presentation. It was very nice, very interesting. Nice also to see someone connecting like the complexity and postmodernism philosophy, at least postmodernism strip of its redundant words, which is about 90% probably, and a process philosophy. But I have a bit of a question about the process philosophy, because I've looked into that once. I think that is a very interesting approach to do something with, but I can never find something really interesting on it, or like read Stanford and entries to those things. It's all still very vague. Like all those people in here, like the postmodernist, it all turns into something very vague, and that's a valid criticism they often receive. Have you read anything about those kinds of things, or the combination between like substance and process philosophy that actually makes sense and tries to like be more concrete and clear about things?
No, it's all nonsense. It's all really, really fluffy. I've had three main people who I've been reading. One is Deleuze, who I've said I find, even though Mahmoud doesn't like him, I find most common cause with just the way he describes things. I like it. Bergson, who talks about very similar things, and most of it, and what I find with Bergson is he's mostly, you realize that Deleuze is mostly ripping him off and using his ideas.
Bergson is cool, and Whitehead is cool, of course.
Whitehead starts off well, I think, but goes off the rails and starts saying that, you know, process is God and God is process. I can't cope with that. And it's all incredibly speculative, which I'm not so keen on. And yeah, I've read Stinger's some of Stinger's stuff on Whiteheads. I had that. I can't remember the name of the book. Just a collection of essays. Apart from that, no, I haven't read anything where I went, oh yes, okay, everything makes sense now. It's like I've come up with this thing, residuality. I've realized this is a process philosophy and it's kind of fluffy, and all other process philosophies are kind of fluffy, and where they do get sharper and more detailed, like for example with Whitehead, then it gets obscure and weird, and maybe I just don't understand it.
No, I guess it's just a very hard thing. But interestingly, you do combine process and objects to some extent in your residuality theory, right? I mean, there are still objects, and they.
Yeah. So what I'm trying to do is I'm trying to say that we're not going to focus on the object. Everything is a process. Everything's in flux, and the residue is a difference, and a collection of differences is how we think about an object. So it's a very different thing than just an object with properties on it. And that idea comes from Deleuze.
Nice. Thank you so much.
Yeah. So yeah, I can't be more concrete than that. Rudy, any question?
Yeah, no question actually. Just a couple of maybe comments if I may. So I like this. Obviously, I need to look into this more. To be honest, I'm also from the software world, Barry, right? And I found this very intriguing. Just one thing, that just an observation. I don't see really. I mean, this is all good, and probably very worthwhile. But probably your concepts and your ideas don't really turn a junior architect into a senior architect, because nobody knows what they don't know, right? And to identify the stressors or the impact, that takes, I guess, experience, right? At the end, I always believe, I'm not sure what you think, software architects, that's obviously a skill to have, but you also need to have, for all this stuff, identification of stresses that you have, all the kind of dependencies that you also depicted very nicely, by the way. That you need to be a domain expert as well. And at the end, you have to assess, the likelihood of an event and its impact, right? Because adding resilience in our business also costs money, right? And at one point, you just need to stop talking about aliens or lizards. So I guess, I mean, this is the only thing, that I would probably say at the end, it is about substance, and about things that are more likely to happen than, because we don't have unlimited resources, right? When we do software projects.
Yeah. And like I said to Shrif, we aren't aiming to solve every single problem. So the stressors that we come up with, the only reason that we come up with them is that that's our path to the attractors. And once we've discovered the attractors, then we can design the residues, and then we can put the residues, it's called contraction, contagion analysis, pull those into an architecture. And the vast majority of the decisions that have to be made are, I think that everyone here has some exposure to Taleb, they're convex things, little tiny things we have to do for potentially big payoff. And for those that are concave, which are big investments, for against things with very small probabilities, then those are things where we have to have a discussion about it, and it has to be an architectural decision, right? We're making an architectural decision that we're not going to have redundancy for this component because we don't have budget for it. And that's an architectural decision that has to be done in sync with people who make decisions about budget, and that budget has to be related to things like income. And absolutely, those are concerns that a junior architect isn't going to think about. And so I teach these ideas to a lot of architects across the world. And one of the first things I'll do is get them to run a little stressor analysis on their current project to figure out, where are you? What kind of architect are you? How mature are you in your practice? And you'll see people with 10, 15 years experience of architecture, and their stressor list is entirely, the server goes down, the queue gets full, someone pulls out a network cable, there's latency in the transatlantic cables, and it's very, very technical, and they haven't moved beyond that understanding of technology. They're still in that little box. Senior architects, they can be people with 1 or 2 years experience, and sometimes they'll go, yes, I know what the architectural implications are if a competitor drops their price. I know where that hits our architecture, I know what has to move, and I know how that's going to impact my work and my design. And so that level of maturity can turn up very, very quickly. And for some people, it never turns up at all. And that can be a factor of what we're interested in and a factor of what we're exposed to and what we get the opportunity to work with. And so introducing these ideas very, very early in an architect's career can help lift them, at least get them to that point faster. And to be honest, that, on a personal level, that's what happened to me. I happened to be in the right room at the right time to hear the kind of these kind of discussions where someone said, look, it's not enough to know how all these components link together and work. You also have to know how money flows through this project. And this is where you go to learn those things. But no, you won't make a senior architect overnight, but you can save someone a considerable degree of pain by exposing them to ideas early.
No, and what about the domain expertise? What do you think about this? Because you just talked about you gave a couple of examples, right? So is an architect is always an architect, as a project manager is always a project manager, or do you think that there is value in understanding, it has nothing to do with software, obviously, but your domain well?
Yeah, so when I teach junior architects, I teach them the concept of fluidity. So as an architect, you might have a concept when you come out of college or from your whatever projects you've worked in as a developer. You might have a concept of what architecture is, and that concept is going to be torn apart by the rest of your career because you're going to be thrown into things which you don't understand. You're going to be thrown into teams where there are competency gaps which you're going to have to cover. And you're going to get the chance to lean into project management. You're going to get to the chance to lean into managing different types of conversation or different types of gap in the enterprise's own understanding of its business. And the most important thing to understand, I think, for junior architects is that what the world they've got themselves into is one of fluidity. They cannot go in with a rigid idea of what an architect is. But I would say that I've got a Hegel comment to deal with here as well. I would say that when you leave a project, you should have domain expertise. It's almost impossible not to if you've actually done the job of an architect and understood these attractors. You might not necessarily have domain expertise on the way into a project. And I say that as a consulting architect who's moved around between many different industries. But once you've done this a few times, you'll find that it's the same set of concerns and the same set of trees that you're shaking in every single case. And so the expertise of an architect is knowing which trees to shake, rather than what kind of trees are these and can I eat this fruit? We'll figure that out along the way.
Thanks for your answers. Just one thing, in the banking industry where I'm actually involved, these guys tried to learn from some of these concepts that you had, this Monte Carlo simulations, the stress tests. I'm not sure if you're familiar with new regulations in the EU, FRTP, where you have to shake your trader's desk, and stress test everything. I think, I just added this, one thing is very interesting, when you institutionalize this kind of methods, what happens is the outcome is very often, unintended consequences. What you have is, everybody does the same kind of stress testing, meaning everybody takes on the same kind of risk. And that makes me a little bit cynical, about my own industry, because I think, at the end of the day, well-intended, but probably, it just leads to the next big blow up very soon.
Yeah, and so one of the first questions I get when I'm teaching classes on this is that architects will say, can you give us a list of stressors that we can use in our projects? And it's like, no, you haven't understood anything. The stressors have to be generated in the environment, in context, and they have to be related to the environment that you're working in. There's no generic list of stressors. There's always some enterprise architect who wants to make everything effective. And so everyone gets to see, and you'll see this if you're working in a large batch, you'll see non-functional requirements come in a spreadsheet that you've got to put a bunch of ticks in. And that's a terrible way to do architecture. Architecture is contextual and has to grow in a context every single time. And so attempts to make it effective are always, as a dangerous, and you bake risk and you bake problems into those things because they're blocking and they're hiding, and you've turned the process into a thing when that happens.
I have a question. I hate to turn this into a technical discussion.
Yeah, but just before this, Shrif, I'll read this comment out loud. Sorry, from Barbara. This also fits in with the idea of diverse sources of information. Differences help expose diverse sets of stressors and therefore attractors. Yeah, interesting stuff so far, to be honest. But Rudy, very good question. And yeah, the institutionalization of these things, it becomes more of a, yeah. Anyway, Shrif, go ahead.
Yeah, so I'm asking Barry, for example, is there, I don't want to ask for an advice or something like that, but is there an application for something like this on a smaller scale, something that really not complex or not too complex? I don't know what is the threshold to define complex systems. For example, I'm thinking about a recent algorithms that I was working on, and it's really all predictable, I think. But sometimes when you read when I meet some error that I'm not familiar with, I'm not sure if this is going to be okay. Yeah, sorry. I'm not sure if this error is something that I should have predicted or should have come up with as a scenario, or is it something complex that I should have run a simulation for? Yeah, how do we define the threshold for complex systems from normal systems that have predefined sets? Is it just lack of domain knowledge, or is there something else that I can work with to just make this distinction? Yeah.
Yeah, so I think that there's a lot of schools of complexity where people try to pinpoint something and say, this is complex and this isn't. This is complex and this is complicated. And I think that our ability to get that right is very, very limited. And so what I tend to do is treat everything as if it's complex. Because you can't go wrong then. So everything is complex. And then I'm going to use these ideas and I run the stressor analysis. And if something is simple, if something doesn't require this kind of effort, you'll find out very, very quickly, because it'll be very, very difficult to stress. There'll be if something is simple, then you've got low N, low K, you're going to have a low number of attractors, you're going to have it's going to be difficult to find stressors to push it around, because the system simply won't move. And if it does move, then you'll say, well, it's not relevant in that attractor. If that particular thing happens, then this project no longer exists. And so it's much easier for me to start out from the perspective that this is going to be complex. I stress it. Oh, hold on, I can't stress it. It's simple. The architecture is simple, and normally that happens within. You can do that within 20 minutes. You'll realize that we're working with something that isn't that difficult, and we just pass that over to a junior architect. In terms of technical failure, there's a bunch of stuff I didn't talk about. Technical failure is the actual relationships between technical components is managed in a different way. That's just standard systems engineering. And in the kind of courses I hold, that's something that I have to test to make sure that architectures have actually architects actually have those skills, that they actually can do systems engineering and capture errors and understand what's going to happen in the technical system. It's not always the case that they can.
Yeah, okay, I understand. Thanks.
Yeah. Cheers, Prab. Oh. Okay. Any other questions? Thoughts? You've got very easy on me.
Cynical comments. Yeah, well, no, because I'm, again, as per usual, before I can start picking on people, I need to absorb and grasp their ideas.
I have a question. Is there like do you have any recommendations for, like you just talked about how different people define complexity and how there are so many different schools of complexity and setting the threshold. Do you have any recommendations in this regard, like something that collects or not lists, but at least discuss some of these complexity thresholds, and I don't know, maybe have some arguments for and against?
Yeah, so two things. The first thing I would do is check out the work of a British researcher called Ralph Stacey. And a South African philosopher called Paul Cilliers, who I mentioned tonight. That's a slippery slope to post-structuralism. But it's very, very good. And he defines very clearly what the difference between complicated and complex is. There's a framework called Kinevin, which if you Google, there's a lot of information on that. It's very popular in management consultant circles, that helps identify different phase states of a complex system in terms of complicatedness or complexity, and that's a great tool to teach. It's one of the first things I teach to architects who are trying to grasp what is complexity. It's very, very, very quick way to get people engaged with the subject.
Okay, thanks. I'll check these out, and I hope you don't mind me bothering you, or I don't know, if LinkedIn or maybe Discord or something. Yeah, because I'm possibly going to text you a lot in the coming time. Yeah, I just hope you don't feel bothered. Yeah.
Yeah. No, not at all. Not at all.
Thanks.
Alexa has asked about a path to criticality on a personal level. I have a slide here where I talk about the stack. And so at the very bottom of the stack, I have the idea of residuality, which is this process philosophy where we don't actually know what's going to happen, and that the future of a system is a function of its residue. On top of that, I have the idea of hyperliminality, Then I have Kaufman's NK model, which we talked about, then the stressor analysis, then the contagion analysis. And when you stack all of these things up, then you have something that you can work with empirically, and that's what my research is. If you pull one of these things away, the whole thing collapses. And so when we're talking about, for example, one of the things that people want to do with these ideas is apply this to the design of organizations. And that's when I get kind of scared, because hyperliminality disappears whenever you're talking about organizations, because the number of potential states, even in a group of human beings, is absolutely enormous. Whereas the number of states in a software system isn't that big. And so hyperliminality, that mathematical leverage that I talked about, disappears very quickly when you have a complex system inside another complex system. And so one of the things that makes me nervous about these ideas is how quickly, in this modern age with Twitter and everything, that people just can pull an idea and apply it to something else. And suddenly someone has a workshop and it'll be called, residuality for personal development, or residuality for organizational design, or residuality for raising cats or something. That sort of stuff is scary, how quickly these things happen these days. And so I'm putting a lot of effort in, as you can see in this stack, into making sure that this is thought through, that even the postmodern stuff, the post-structural stuff is brought to bear, and it's clearly defined, and it's falsifiable, and scientific. And if you're going to do this kind of thing, move residuality to another domain, it has to be done. I would like to see it done with the same care and the same cautiousness to make sure that things actually remain in the scientific realm. So, but I mean, if you're just doing it personally, then you go for it. I mean empirical. I mean that it can be proven. Oh, that's a joke, right? I like this. I want the work to be reproducible, replicable, and I in software, there's a tendency to latch on to an idea that's semi-coherent and lift that idea up and reify the idea. And of course, I'm talking about agile, right? And there's no scientific foundation to show that it actually works. There's no way to falsify it, and it becomes a cult. And so I want to keep this out of that particular realm. Yeah, in saying that, the actual the stressor analysis and those things, that there's an anything goes kind of Feyerabend feeling to that. Let's throw probability out of the window. Let's throw cause and effect out of the window. There are rules to the stressor analysis which we don't have time to go into. Anything that anyone says has to go in there. You're not allowed to take anything away. It is a bit lawless for a while, but then we have to settle down and do real work at the end of it all. Okay.
So Barry, can I just, last question maybe for me. So do you really think, that this, and I really want to know this out of practice, right? When you talk with juniors resources, does this make a difference? I mean, you conceptualized pretty much your inner workings, that made you successful as a software architect. That's excellent, right? But do you think, this kind of stuff can be really taught, or is it a shortcut, to, I mean, you said it earlier, right? Did you see this in action? Do you follow normally your students, and how this makes a difference? The framework itself?
Yeah, it does. It does make a difference. It makes a difference to how people approach problems, to the level of confidence they have in making decisions. And it makes a huge difference if there's more than one of them. If there's a team of architects and they're all thinking in this way and they're all communicating in the same way, it makes a huge difference how quickly they get work done and how concretely they can share ideas with each other. And so the impression that I get from talking to people who've been exposed to the ideas and then spent time doing them is that it completely changes their practice and makes things easier for them. Obviously, there's bias in that because they're reporting back to me. But it seems to be quite positive. Yeah.
Okay. Very good. Thanks.